All right, good evening, everybody. How's everyone doing tonight? Good, good. You're not melting, or at least you're not anymore, so welcome to the cool Dyer Observatory Library. So I'm Dr. Billy Tietz. I'm the director here at the Dyer Observatory, and it's my pleasure to welcome you all to the July Meet the Astronomer lecture. Before we begin, I just wanted to take a couple moments to talk a little bit about Dyer, because I know we've got a lot of newbies here, and we love our returning folks, but we love our new folks as well, so welcome to everybody. But over the past year, Dyer has been really committed to expanding our educational outreach into the community, into schools, and also continuing to expand the capabilities of this very unique site. So this past school year, for example, we welcomed nearly 1,000 K through 12 students. A lot of those were MNPS students, and we also worked with the fifth grade faculty to establish a curriculum for the field trips that our fifth graders come out here to experience, so that they can actually tackle some of those science standards that they're going to be learning. We also just completed a teacher workshop for K through 12 teachers that really helps to equip them a little bit more in terms of learning about microelectronics and workforce development. So that was a really successful workshop, and we were proud to be a partner in that, along with Indiana University. And we want to do even more with our K through 12 students and just the community at large. And one of the things we're planning on doing is fundraising for an inflatable planetarium, a really nice digital state-of-the-art planetarium that not only would be used here, but we'd be able to take it out to schools and other community centers. So as you're walking around tonight checking out the exhibits, there's QR codes hanging around, so if you want to donate a little bit, we'd love to have you donate that. Or folks that are watching from YouTube, we've got links on our website as well. So if you have any questions about that, you can always come in and ask me there. We've also got, so keep an eye on our website and our social media, because we have a lot more events coming up this year. We've got more Meet the Astronomer lectures. I think we've got 4 more scheduled so far. Telescope night, if you've never been to a telescope night, those are really fun, especially when it's clear, because you get to actually see some stuff. We're going to have Saturn back in the October sky, so everybody's looking forward to that. It'll probably be cloudy that night since I said that, but who knows? We'll keep our fingers crossed, right? We've got Bluebird on the Mountain concerts. We've got Opera on the Mountain in September. So all of our ticketing we do through Eventbrite, so go to our homepage and click on that events and ticketing link, and that'll take you to our event listings. And there's a convenient little follow button on there as well. If you click that, you'll get a notification whenever we add something to our website, and tickets typically go pretty fast. So it's a convenient little reminder as well. So for the program tonight, it's going to last, about 45, 55, 95, however many minutes you want to talk, right? Typically about 45, 55 minutes. And then we will open up the floor for questions. And folks that are watching live on YouTube, get a question, go ahead and pop it in the chat, and we're going to get to as many of those at the end of the program as well. So just kind of hold, for the rest of us here, just kind of hold your questions until the end. And then we'll finish the night off by going up to the Seaford telescope. It's probably going to be cloudy, unfortunately, but we've still got our fingers crossed. But even if it is cloudy and you've never seen the telescope, it's really cool. So we'll have folks up there that can tell you all about it. But we are here to hear and see Dr. Marcelo Disconzi. So he is an associate professor of mathematics at Vanderbilt University. He earned his PhD in mathematics from the State University of New York at Stony Brook in 2012. And he works on mathematical aspects of general relativity and fluid dynamics, with a special focus on how gravity and fluids interact with one another. I can't even comprehend what that sentence really means, so you may have to ask him afterwards. He's a recipient of numerous awards, including the 2018 Sloan Research Fellowship and a 2023 Chancellor's Faculty Fellowship. He's the author of more than 50 scientific articles, the upcoming book, Relativistic Viscous Fluids, and the book, Who Me? I'm a Mathematician Now. And that latter one, I have a copy of it here. This is for 8, 9, 10, 11, 12-year-olds that are interested in science and math. There's a whole series of these, but Dr. Disconzi wrote this one, and it's basically him telling his story of what it was like when he was that young age, what he was thinking. What did he want to do with his life? So folks that are, that age and are wondering, what am I going to do when I grow up? They can kind of see what an actual mathematician was thinking at that time. So they're a great read. There's a whole series of them, so be sure to check that out. One thing I also want to mention, he will come to your school and do presentations. So if you're interested in that, come talk to him after the talk tonight. One more thing about that book. I'm a mathematician now. So a lot of you that are attending tonight, there were tickets at the front for a drawing for one of these books. We're going to be giving away 5 of them this evening. So after the program, after we do the Q&A, we're going to do the drawing for that. Okay, so keep your fingers crossed and maybe you'll get a copy of this. And if you're not lucky enough to get a copy, you can get them at many booksellers, okay? And they're a great read. So with that, I'm going to turn it over to Dr. Disconzi, and we're going to sit back, get comfy, and learn a little bit about Einstein's equations. All right, let's give our speaker a big round of applause for being here.
Is this on? Okay. Just a little comment on visiting schools. Is that okay? Yeah. Just a little comment on visiting schools. There is no fee for that. That's part of the outreach that I do with the math department. So I'm open to visit schools and talk to kids about math and science and have fun. Okay. So I want to thank William for the invitation and the audience for being here. Today we are talking about Einstein's equations. So if you look at the picture here, you see Einstein writing his famous equations on the blackboard, the meaning of which I'm going to explain in this talk. And if you look carefully, it's a bit blurred the image, but he puts a question mark here, like asking if this is true or not. And this question mark can be interpreted in different ways. If you are an astronomer, one question you might be asking is, what kind of observations I can make based on these equations. But as William told you, I am not an astronomer, I am a mathematician. So for a mathematician like me, this question mark could mean something like, can these equations be solved? How do we find solutions to these equations? So Einstein equations, they are the fundamental equations of the general theory of relativity, GR. If you ever heard about Einstein equations or general relativity, you probably know they are about gravity. And before Einstein, gravity was described by Newton's laws of gravitation. Newton's fundamental insight into the nature of gravity is that the force that makes an apple fall to the ground is the same force, I just found a typo on my talk, of course, is the same force that keeps the moon orbiting the Earth and the other planets orbiting the solar system. So exactly the same force that makes an apple fall to the ground is the same force that keeps planets orbiting the sun. And Newton did more than that. He wrote down a formula to calculate the force of gravity between two objects. I'm not going to write down the formula here for you, but I'm going to highlight one of its key aspects. It says that any two objects attract each other with a gravitational force proportional to their masses. Mass is basically the amount of matter, the amount of stuff that you have in a body. And that's what we usually measure in pounds or kilograms. Proportional here means that the greater the masses, the greater the force. So for example, the gravitational force between the Earth and the Sun is greater than the gravitational force between the Earth and an apple, because the mass of the Sun is larger than the mass of an apple. And I want to stress this word here, any. So it doesn't matter what these objects are made of. All that matters is their mass. And then there's going to be a gravitational attraction between them. In other words, gravity is universal. all objects feel a gravitational attraction. And again, it's an attraction. There is no such thing like a repulsive gravity. Okay, it's always an attractive force. Let's imagine the following situation. Okay, you are here standing on the surface of the Earth, and you are being constantly pulled toward the center by the gravitational force. The gravitational acceleration on Earth's surface, which is the rate at which objects fall to the ground, the rate at which they accelerate under the gravitational force, is equal to 32 feet per second square. Don't pay attention to this number or these units, okay? They're not very important. What is important is to know that there is a gravitational acceleration, the acceleration caused by gravity on the surface of the Earth. Let's call that acceleration g, okay? Now, despite the gravitational force, we are not falling through Earth. That's because there is another force countering the force of gravity caused by the ground, causing a force upward that counteracts the effects of gravity, right? And that's how a scale works. When you step on a scale, the gravity is pulling down, but then there is this counteracting force of the scale on your feet, and that's why the scale can record your weight, okay? Because there is a reaction to the force of gravity caused by the scale. Now let's imagine the following situation. You are in a spaceship far away from any planet, any solar system, so there is no gravity, okay? There is no gravity, no gravitational force. But let's imagine that this spaceship is accelerating at exactly the same rate as the acceleration that you feel here on Earth due to the gravitational force. That's what that I'm calling g. If you're inside the spaceship and you step on a scale, the scale is going to accelerate towards you. There is no gravity, so you're like floating in space, but the scale is going to accelerate toward you with the motion of the spaceship. And it's going to cause a force on your feet that's going to counteract the force exerting a force on the scale. So the end result is that the scale is going to record your weight exactly like it does here on the surface of the Earth. Okay? Moreover, if in the spaceship you drop an object, there is no gravity, so the object is going to float in space. But because the spaceship is moving, you're going to see the ground of the spaceship moving toward the object, right? At this accelerated rate. But from your point of view, because you're moving with the spaceship, what you're going to see is the object falling toward the ground. And you're going to see it falling at exactly this rate, which is the rate that objects fall to the ground here on the surface of the Earth. In other words, these two situations are indistinguishable. You cannot distinguish gravity from a uniform acceleration. Okay? So if you didn't know you were in a spaceship, let's say aliens abducted you, right? You wake up there, like, as far as gravity is concerned, you'd think that you are on Earth. Okay? Everything would look the same. But now let's look at the opposite situation. Again, you are on a spaceship, there is no gravity, but now the spaceship is not accelerating. So you're just going to float weightless in space. Okay, just going to float in space. And finally, imagine that you are back on Earth and you are in an elevator, but the cables of this elevator is snapped. So this elevator is free falling to the ground. As the elevator is free falling, you are going to again feel weightless. And if you didn't know you were in a falling elevator, well, you're going to soon find out, but if you didn't know before, you might think again that you're in space. I'm just floating like in the vacuum of space. In fact, as you might know, that's how astronauts train for their missions in space. They go on a plane, this plane goes high up and then drops in free fall, and while the plane is dropping, the astronauts experience this weightless sensation. So let me play a little video here for you showing this experiment that people do on a plane. So the video is long, it has a lot of interesting things, explains the science really well, but I just want to get to the point where you have this weightlessness, so you can see.
I don't know, I had concerns before I came in, silly concerns about flying and maybe feeling sick or anything, but now that I'm in here and actually doing it, that feeling when you become completely weightless, it's like nothing else. I could do this just all day long. Oh. The instinct is to wind the windows down, but it does nothing for you. Just the gentlest touch off the roof will just fire you straight over. Everybody's got this look on their face.
Pretty cool, right? But again, this is not in space. This is on an airplane here on Earth. Just the airplane is on free fall, you know, and that is giving the sensation of being weightless, which is how they train to be on space. So the lesson here is that the natural state of gravity is free falling. The natural state of gravity is weightlessness. That might sound a bit counterintuitive because we don't experience gravity like that every day, but that's because every day there is always a force countering the force of gravity, which is the force exerted by the ground on our feet, and that's why we're not constantly falling to the center of the Earth. Okay? But the pure state of gravity is free falling. It's like this weightlessness condition. Now, let me make a remark, and I'm going to make a few of these remarks during the talk. These are some technical remarks. What I said here about that gravity cannot be distinguished from a uniform acceleration, that's not exactly true, but it's close enough to be true for the sake of this talk. Okay? And then, if you are interested in the details, I'm sweeping some details under the rug here for the sake of time, but you can ask me at the end, and you can go back and discuss some of the technical details of this statement. Now, this phenomena that we just saw about gravity, they raise some very interesting puzzles. We know 4 forces in nature: gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. And of these, only gravity is universal. Only gravity is felt by all objects as an attractive force. For example, for the electromagnetic force, if you have 2 positive charges, 2 equally charged particles, they're going to repel each other. If you have opposite charges, one positive and one negative, they are going to attract each other. And if you have particles that are not charged, they are neutral, then there is no attraction and no repulsion, then nothing happens. These other forces, the strong nuclear and weak nuclear force, they are related to nuclear physics. I'm not going to explain them, but what you need to know is that like the electromagnetic force, they can also behave in different ways. They behave in different ways depending on the properties of the particles. So only gravity has this feature that every object feels it the same way. So it's universal. And of all these forces, only gravity can be quote-unquote mimicked. For example, we cannot fake the electromagnetic force like we do with gravity using a spaceship, like I was explaining before. Nor would we be confused about having or not an electromagnetic force like what happens to gravity in the free-falling elevator scenario. So what I'm trying to say here is that gravity is very different than the other forces. Now, strictly speaking, there is nothing wrong with gravity having these unique features. But a general philosophy in physics is that when you see something very special, that requires an explanation. Okay? As an analogy, for example, I came here today and I see people dressed in all sorts of different clothes and colors. That's fine, nothing special. But if somehow everybody was dressed in purple, I would say, there must be a reason for that, right? And that's like the thinking goes for physicists. Special phenomena require an explanation. Okay, so there should be an explanation for these unique features of gravity. And in what he called his happiest thought, Einstein offered the following explanation for these puzzles, the following explanation for these unique features of gravity. Gravity is not a force. Rather, it is a manifestation of the curvature of space. Okay, there's a lot to unpack here, so I'm going to explain this in more detail. Let me start with this word curvature. We're going to spend some time talking about curvature later today, but I want you to follow your intuition, and I want you to think that curvature is what you think it is. Okay? So, for example, if you see a table like this, you would say that this table is flat, has no curvature. But the surface of a ball, like the surface of a basketball, is curved. Okay? And we're going to get into more details soon about what this means. But what about masses? Remember, Newton told us that if we have, for example, the sun and the earth and the earth are attracting each other with a gravitational force proportional to their masses. But if you look at this statement here, there is nothing here about mass, right? What Einstein explained is that masses, yes, they do play a role as follows. Massive objects, they deform, they curve the space around them. So, for example, if you look at the Sun-Earth system, the sun is this very massive object, so it curves space around it, which is illustrating the picture by this valley here underneath the sun. And there is no force between the Earth and the sun. The Earth is just traveling by inertia. So the Earth is just minding its own business, traveling by inertia without feeling any force. But because space itself is curved, it can happen that this inertial trajectory of Earth is a closed curve. And that's how the Earth is orbiting the sun according to Einstein's theory. Think like this. In a flat space, like in this picture here, if you throw an object and there is no force, this object is going to simply travel on a straight line, like this line here. However, in a curved space, like in this picture here, if you throw an object, the object is going to follow a trajectory that follows the curve of space, like in the second picture here. And what I'm going to do next, I'm going to try to explain curvature in more detail, but before I do so, let me just tell you why this idea of Einstein solves the puzzles about gravity that we saw before. First, the universality. Well, if gravity is not a force, it's just a manifestation of the curvature of space, then it's kind of natural that it's universal, because all objects are objects in space. They live in space, so they're just experiencing a feature of the space shared by all objects. That explains the universality of gravity. As for the rocket experiment, well, again, if you're just following a trajectory on a curved space, there is something particular about your motion. And then it's not very surprised that you should be able to mimic this motion with a rocket. Just adjust your rockets in certain way to mimic the motion that you would experience traveling in a curved space. And finally, for the elevator experiment, well, there is no force in either case. There is no force when you are on space, but in free falling, right, you would say that you're only experiencing gravity, but the gravity is not a force, so there is no force there either. So in either case, there is a force. So that's how we explain these puzzles of gravity according to Einstein's theory. I'll have to make another disclaimer. Every time that I say space, if I were to be very precise, I should be saying space-time. But for the sake of time, I cannot explain space-time to you today. And it's not very important, because the fundamental concept that we are going to be tackling now is this concept of curvature. And for that, it suffices to talk about curvature of space. Okay? So let's talk about curvature of space. Let's go back to our intuition that we have this table here. You say it's flat, has no curvature, and the surface of this ball that you say that's curved. One difficulty that people have when they first learn about relativity is the following. They think, okay, this ball, the surface of the ball is this two-dimensional object, but it's sitting inside the three-dimensional space. So that's why it can curve, it can bend, because there is an extra dimension, there is a space to cause things to bend and curve inside the space. But then, if you think like that, the question is, how can the space we live in itself be curved? Does it not need a larger space inside which it can bend, like the ball does? So that's like one of the main difficulties people have when they first hear about this idea of space being curved. How is that possible? Don't we need an extra dimension so that you can fold things inside this larger space? And part of the problem here is that when you draw pictures to illustrate things for pedagogical reason, we always draw a picture of a two-dimensional object curving inside a larger three-dimensional space. But that's just a way of visualizing things. What I want to explain to you next is that it is possible to talk about curvature without referring to a larger space. We don't need to have one object sitting inside a larger space in order to talk about curvature. And then once you understand that, then it becomes clear how our space, the space we live in, can be curved. We don't need an extra dimension for that. Okay, so let me start with a two-dimensional plane, like the screen projecting the slide here. On the plane, if I want to take, I take 2 points and I want to find the shortest distance between these 2 points, well, that's just a straight line, the shortest distance. And there are some other features that are unique to the two-dimensional plane. For example, if I draw a triangle, where the angle between these two sides is 90 degrees, I know that necessarily the other two angles, they have to be less than 90 degrees, because the sum of all angles of a triangle on the plane has to be equal to 180 degrees. So if one is 90, the other two, they have to be less than 90. Okay, this is a feature of triangles on the plane. But now let's think about a two-dimensional sphere, like the surface of the Earth. Okay? And I want you to think really like Earth's surface. Don't think of the interior of Earth, and don't think of the space above, just the surface. So if you look just at the surface, that is also a two-dimensional object, like the plane was two-dimensional. But the features of this two-dimensional object are going to be very different than those of the two-dimensional plane. Suppose you want to travel from the North Pole to the equator, to a point on the equator here, through the shortest trajectory, the shortest path. Well, what you do, you're standing on the North Pole and you just walk straight, right? Just walk straight, you don't turn left, don't turn right, walk straight. That's going to give you the shortest trajectory to get you to a point on the equator. Now, of course, from your point of view, you are walking straight, but in reality, you are walking through a meridian, which is a curved arc on Earth's surface, like this red curve here. Right? So that's telling us that the shortest distance between 2 points on a sphere is an arc, is not a straight line. If you think about it, you cannot even have a straight line on the surface of the Earth, because you're going to always have to move outside the surface. And there are other features that are different than what you saw for our two-dimensional plane. For example, if I draw a triangle by joining the North Pole to the equator by this meridian and this meridian, then this angle here is 90 degrees, this angle is 90 degrees, therefore the sum of the angles of a triangle on the sphere can be more than 180, because you get 90 plus this third angle here, which is going to be some positive number. So the punchline is that the geometry of a sphere is different than the geometry of a plane. Okay? That's because the sphere is curved. The sphere has curvature, and that's what makes the geometry of the sphere different than the geometry of a plane. Now, that's not very surprising, because the Earth is not flat, right? So they are not flat, so that's why the surface of the Earth has curvature. But then again, comes back to that point that I raised before. You might think, okay, the surface of the Earth can be curved because it lies inside a larger three-dimensional object. So what I want to explain next is that this behavior of having curvature or having shortest distances that are not straight lines can happen for a two-dimensional object without ever referring to three dimensions. So that's what I want to explain next. So let's imagine that this rubber ball represents the surface of the Earth and the hexagons represent curved trajectories on the surface. Then with a flashlight, I can project these hexagons onto the flat two-dimensional table, the flat two-dimensional plane. And if I do this very carefully, I'm going to get here with the shadows a distorted but otherwise faithful representation of the surface of the Earth, of these hexagons. So here is a schematic picture of this video. Imagine that the yellow lines represent the light rays. So for example, when you shine the light rays, this triangle here on the sphere is projected onto this triangle here on the plane. Okay? And in fact, that's what we do when you draw a map of the globe, right? You take the two-dimensional globe and project onto a flat piece of paper. That's how we draw a map of the globe. Now, if you look at this red curve here, that's going to be the shortest distance between this point on the equator and the South Pole. When you project this curve on the plane, it's going to be projected on this arc here on the plane, okay, this purple one. Incidentally, that's why if you look at the trajectory of an airplane on a map, it's not going to be a straight line, because the straight line is the shortest distance on a flat plane. But the airplane is trying to take the shortest distance on Earth's surface, which in general is going to be an arc like this one. So when you project this trajectory onto your map, you're going to get a curved trajectory like this, right? But now, let's do the following. Let's forget about the sphere for a moment and focus only on the projection. Focus only on the shadows that you obtain from this sphere. Now, as I said, these shadows, they are a faithful representation of the geometry of the sphere. So if I'm thinking in terms of the geometry of the sphere, just written on the plane like we do with a map, the shortest distance between these 2 points is going to be an arc like this, not a straight line. And this triangle is going to have angles that add to more than 180 degrees, right? 90 plus 90 plus this third one. So here I have like a copy of the geometry of the sphere, but now this copy is only on this two-dimensional plane. So the important thing, oops, here we go. So the important thing is that we have this curved geometry on the plane. We know that it's curved because it's a copy of the geometry on the sphere. The shortest distance between points is given by arcs, not straight lines. But the plane doesn't know about the third dimension. You don't have to think about the third dimension to describe this curved geometry on the plane. So you can describe it entirely intrinsically in terms of two dimensions. And now we're going to do something even more interesting. We're going to build a new geometry in the following way. I'm going to declare by definition that lines on the plane obey the same rules as the shadows obtained by projecting lines from the sphere. In other words, I'm going to define that the shortest distance between points on the plane is going to be exactly the same that you get on the sphere, which means not a straight line, but curved paths like this. And if I do that, as I said before, I'm going to have a geometry that's faithful to the geometry of the sphere. I'm defining it to be faithful to the geometry of the sphere, so it's going to be a curved geometry. Now, I know you have questions. Can we do that? Can I just make up rules, say that now, from now on, the distance is going to be given by arcs and not straight lines? Yes, we can. I'm going to explain this next, because this is, I think, one of the most fundamental ideas in mathematics, which sometimes is not explored enough when you talk to the general public. I want you to think about the rules of math as the rules of a game. So if I ask you, why is a touchdown worth 6 points? Well, because people who created the game decided so, right? But they could have as well decided that a touchdown is worth 4 or 8 points, whatever we want. So we can create new games, new football games, with any rules we want. There are basically only 2 principles that we have to observe when you create these rules. First, the rules have to be self-consistent. I cannot say that a touchdown is worth 6 points and 8 points at the same time. I have to pick one, okay? Have to be self-consistent. And second, when I pick my rules, I have to stick to them. I cannot change the rules in the middle of the game, right? And the rules of mathematics are the same, okay? We can create a geometry on the plane based on rules where the shortest distance between 2 points is a straight line, like we do in standard geometry that we learn in high school or in college. But we can also make the rules such that the shortest distance between points is an arc, not a straight line. And that's going to give us a curved geometry. But remember, we have to be self-consistent. We need to pick one. I cannot say that is at the same time a straight line and not a straight line. I have to pick one. Okay? Now, let me make a very important observation. I'm not saying that you can make up that 1 plus 1 is equal to 3, okay? I don't want anybody saying like, oh, the math professor said that we can make up rules like 1 plus 1 is equal to 3. No, you can't. And the reason why you cannot is because when you compute to 1 plus 1, you are using the rules of arithmetic. And the rules of arithmetic have already been set for you. Remember, you cannot change the rules in the middle of the game. Okay? You can create other numerical systems with different rules, but that numerical system is not going to be arithmetic. And when you go to school and you are tested, you are being tested on the rules of arithmetic. So that's why 1 plus 1 has to be 2 and not 3. So now the punchline is that we can create a geometry on the plane that's curved without ever referring to a third dimension. So we can talk about things intrinsically. We don't need a larger space. And then everything that I said about 2 dimensions applies equally to 3 dimensions, 4 dimensions, any number of dimensions you want. Once you know that you can make the rules to create a curved geometry without referring to a larger space, you can do that in any number of dimensions. And that explains how our space, the space we live in, can be curved without having a larger space sitting within. But now, if you think about what I just told you, we can make all these different rules, so we can have actually infinitely many different geometries. We can create infinitely many different geometries, each geometry with its own rules. So I want to pause for a second to stress this, because that's the point I mentioned that I think sometimes is not communicated enough to people. In the empirical science, we are bound by the laws of nature, right? If you do physics, chemistry, biology, you have to obey the laws of nature. You can create new theories, but if our new theories do not reproduce what you see in the real world, we just throw them away. Not in mathematics. In mathematics, we can do anything that we want as long as you are self-consistent and we stick to the rules. So that's why I said that mathematics is the freest of sciences. We are bound only by self-consistency and our imagination. Okay, that's a beautiful thing about mathematics that I think sometimes is not communicated enough. Okay, I know that I gave a lot of information, so let me give you some recap. First, gravity's unique features make it very different than other forces in nature. Okay, and the idea that physicists have is that these special features of gravity require an explanation. The explanation given by Einstein is that gravity is not a force at all, but is an expression, a manifestation of the curvature of space. And curvature is caused by the presence of matter. Massive objects curve space. That's what causes the curvature. We also saw that we can talk about curvature of space without having it sit inside a larger space, which in particular tells us that it makes sense to talk about our space, the space we live in, being curved without referring to a larger dimensional space. And we can have different kinds of geometry. As I said, okay, well, it's my bedtime. So you can have different kinds of geometry, right? So we can create all these infinitely many different geometries if we want. However, physicists, they're not interested in these infinitely many different geometries, right? These are mathematical constructions that they don't care about. They are interested in the geometry of our universe. So physicists, they want to answer concrete questions like, how do we know the curvature caused by the sun, by the earth, etc.? So how do you answer this question? Here's the sun. It curves in space. How do you calculate that? How do you know the curvature caused by the sun? And the answer, is the theme of this talk, is going to be given by Einstein's equations. So without further ado, here they are, Einstein's equations, right? Now, before you look at this and you think, oh, this is too complicated, I don't understand, what the heck is this? Let me make some remarks. Think of math symbols, especially the math symbols in this formula, as a language we use to express mathematical concepts, okay? Math symbols are like a language we use to express mathematical concepts. And in that sense, it's not very different than some other language that you may or may not understand. For example, if you don't know Mandarin, you have no idea of what this is saying, right? For me, this sentence here is much easier than these other sentences because I know the language of these math symbols, but I don't know any Mandarin. In fact, I don't even know if this is really Mandarin. I'm just trusting the internet, okay? It is? Okay, great. Yeah. So the point is that, again, this is like a language, right? So if you see some expression in Mandarin, well, you might say, okay, that's, again, maybe you don't know if it's Mandarin. You might say, looks like some language in a Chinese family. I don't know the language. I don't know what it's saying, but it's fine. I bet you would not be saying, upon seeing this, oh, that's complicated. What the heck? I hate this, right? Like people do with math sometimes. So next time that you see a math formula you don't understand, don't freak out. Just remember, that's just a language that you don't speak, okay? And that's fine. How many of us speak more than one language anyway, right? That's completely fine. But now, if you don't speak a language, what you can do, you can ask somebody to translate it for you. So here's Google translating it for me. Okay. And again, I'm just trusting Google. So now let me translate Einstein's equations for you. Okay, let me translate Einstein's equations for you. Remember, Einstein's equations is related to mass creating curvature. So the left-hand side of this equation here is the curvature part. So this is something that expresses curvature. And the right-hand side of this equation encodes the distribution of matter. The objects with mass are on the right-hand side of the equation. So this is basically saying that if you have mass, matter, objects with mass, that creates curvature. That's what Einstein's equations are saying. So that's the translation that I'm giving to you. Now, if you want to get into the details of, okay, but how much exactly is the curvature? If I have the sun or the earth, if you want to get to the details, then you have to start getting into the specifics of this language. But again, that's no different than some other written or spoken language. If I want to get into the details of what these symbols means, that symbols means, of the characters, then I have to go and study the language. But if I just want a big idea of what it means, that's what Einstein's equations are telling us. The presence of mass creates curvature. So we spent some time talking about curvature, math symbols, so now we're going to go back to physics and answer the following question. How is Einstein's theory different than Newton's theory? In the end, what do we gain about thinking of gravity in terms of curvature? Okay, there must be an advantage to introduce this new theory, right? And I'm going to do that. Before I do that, let me just make two further disclaimers. When I say curvature, to be precise, I should say a type of curvature, because there are different types of curvature you can define, and there is one that's specific for Einstein's equations. And when I say matter, I should really be saying matter and energy. That's because of Einstein's other famous formula, E equal to mc squared, that says that energy and mass can be converted into each other, okay? And finally, if you look at this equation here, it looks different than the equation we had in the first slide with Einstein, right? But those are just different ways of writing the same equation, okay? One phenomenon that can be described with Einstein's theory of gravity but cannot be described with Newton's theory is what we call gravitational lensing. So imagine here you have an object with large mass, a massive object, could be, for example, the sun. And behind it, you have a source of light, could be a star. When the light travels from this star and passes near the sun, it's going to follow this curved trajectory, because, again, the sun is curving the space around it, so the light is going to follow a trajectory that's curved when it passes near the sun. However, here on Earth, all that we can see is the light that reaches us, right? So if we were to trace this light backwards on a straight line like this, we would think that it's coming from this point. We would think that it's coming from this point, where in reality it's coming from this point, okay? So that tells us that the objects in the sky, they might not really be where they seem to be, okay? Because the curvature of space is deflecting the light rays. And if we just trace back as a straight line, we are going to miss where they come from. This, in fact, is a real phenomenon. This is something that astronomers measured with telescopes, okay? In fact, this was one of the very first predictions of Einstein's equations that people confirmed in 1919, and this helped prove that, or corroborate Einstein's theory of relativity, okay, this gravitational lensing phenomena. Let me give you another example of gravitational lensing. Okay, so this is the first image of a black hole captured by the Event Horizon Telescope in 2019. A black hole, as you probably heard, is an object where that curves the space so much that not even light can escape from it. Okay, so what you see here is not really the black hole. You couldn't, because the black hole is black, light cannot escape. What you see here are the hot gases around the black hole. And let me explain how this picture here is also due to gravitational lensing. So let me show you a video here. So you have this black hole that is curving space around it a lot. So when lights pass near the black hole, they're going to follow some curved trajectory, like we saw before. So all these light rays are going to come, they're going to follow these curved trajectories, and I'm going to give an image that's going to be seen in our detectors, like this image here. So this explains the image of a black hole captured by the Event Horizon Telescope. But things become more interesting. There are certain light rays that actually make a half orbit around the black hole, because the curvature is so intense that they make a full half orbit before reaching our detectors, like this. In fact, the curvature over near a black hole is so extreme that there are certain trajectories of light that make a full orbit around the black hole before reaching our detectors. They do a full orbit and then can be detected here on Earth. So in the end, with all this gravitational lensing, they're going to produce an image that's going to look like this. Okay? So this is the image of a black hole captured by the Event Horizon Telescope, but in addition, you see this very thin ring of light here, okay? Coming from these orbits that make half or a full period around the black hole. This ring of light has not been measured yet, okay? So that's just a theoretical prediction, but there is a plan to launch a space mission called the Black Hole Explorer to actually measure this very thin of light. Okay? So that's going to be one of the most stringent tests of general relativity. So people are really excited about that. Now let me mention that this video is not make-believe. Okay? So these trajectories are computed by actually computing the curvature caused by the black hole, and they are computed using Einstein's equations. Okay? So let's talk about solving Einstein's equations. So I already told you the basic story. Conceptually, we understand now what Einstein's equation mean. They say that if you have a distribution of matter, objects with mass, that causes some curvature. Okay? So we can now understand what Einstein's equations are telling us. However, understanding an equation is different than solving an equation. Right? An equation can be easy to understand. It can be very hard to solve. Okay? So now we understand conceptually what Einstein's equations mean. Doesn't mean that we can simply solve it. In fact, Einstein's equations turn out to be very hard to solve. For this, let me give you an example. Okay? Suppose I give you this equation here. 2x minus 10 equal to 0, and I ask you that question, solve for x, right? So like when you're back in school, you have to solve for x. That means I'm asking you, what is the value of x that I have to plug in this equation to make the left-hand side equal to 0? And this is something we learn in school. I think you know the answer to this one is x equal to 5, because if I plug 5 here, I get 2 times 5 minus 10, that's 0. But now let's look at this equation. And suppose I ask the same question, solve for x. Now, you might think that this is a very different type of equation, but conceptually, they are the same kind of equation. Both are equations involving what you call polynomials in mathematics. Okay? And in fact, this question, solve for x, you can easily understand what it means. If I ask you solve for x, you understand what I'm asking you to do, solve for x in this equation, just that it's much harder to do than in the first one. Okay? But conceptually, you can understand what the question is asking you. Okay. But now, if you stare at this second equation long enough, you can realize something. Whatever x is, and we don't know what x squared is always non-negative, because if you take a number and you square, meaning if you take a number and multiply by itself, you get something that is non-negative, is greater or equal than 0. Similarly, if you take a number and raise to the power 4, which means if you multiply a number by itself 4 times, that's what it means raised to the power 4, you also get something that's non-negative. Okay? A number times itself 4 times, whatever the number is going to always give you something non-negative. In fact, if you take any number and multiply by itself an even number of times, 6, 8, or 10, you always get something non-negative. So all these powers of x here are non-negative. Okay? And then what we are doing, we are taking these non-negative numbers and multiplying by some positive numbers, 3, 11, and so on, and adding them up. So whatever x is, this expression here is non-negative. It has to be greater or equal than 0. Okay? Because I'm just adding non-negative numbers. And then I do the following. I take this non-negative expression and add 1. I'm increasing a non-negative number by 1. Okay? So again, I don't know what x is, but whatever it is, I can say for sure that the left-hand side of this equation is always positive. Okay? Because I'm just adding a bunch of non-negative numbers, and in the end, I add 1, increase by 1. But I think you see the problem now. If this is always positive, it cannot be 0, right? If it's always greater than 0, it cannot be 0. So it's impossible to find x in this equation. It's impossible to find an x that's going to make the left-hand side equal to 0. So this equation has no solution. Now, this might seem strange, but there's nothing wrong with an equation having no solution. Many equations don't have solutions. Okay? Just, you might not have seen them because in school, when you give an equation to solve, you typically give an equation with solutions, right? Imagine a malign teacher, like, give an equation like you can only live now when you solve this equation, right? No, we don't do that. But now let's go back to Einstein's equations. When you're trying to solve Einstein's equations, what you're trying to do is trying to find the geometry of space. We are trying to answer the question, given a certain distribution of matter, what is the curvature? So it is more complicated than solving for x. You're trying to solving for another kind of object, the geometry. But the same principle applies. This equation may or may not have solution. Okay? I just gave an example of an equation without solution. It could be that Einstein's equations have no solution. So that's the question. Do Einstein's equations have a solution? Right? And here is a point where mathematicians and physicists think about Einstein's equations differently. A physicist is going to look at this equation and is going to ask questions like, okay, what happens if the amount of matter here is very large? Is that going to create a black hole? Does it make a difference if this matter has an electric charge? Does that affect the curvature or not? Things like that. But a mathematician is going to say, wait a minute, how do we even know if we can solve these equations? And if you cannot solve, which means you cannot make the left-hand side equal to the right-hand side, that means that this story that I've been telling about matter causing curvature is not correct, because that story is based on having the left-hand side equal to the right-hand side. In other words, if we don't have solutions to Einstein equations, we don't have the correct physics, right? So this cannot be an expression of a fundamental law of gravitation. So this question about do Einstein's equations have a solution is fundamental for physics. Okay, so that's our question. Do Einstein's equations have a solution? And the answer is yes. The answer is yes. And that was established by the mathematician Choquet-Bruhat in the early 50s. Okay, so she provided an affirmative answer to the solvability of Einstein's equations. Okay. Now, for the sake of time, I cannot explain exactly what she did, because that would require me to explain what it means, what it really means to solve Einstein's equations. But you should keep in mind what I told you before. Okay, so if the equations had no solution, then they could not be an expression of fundamental laws of nature. So no solution, no physics. And this result is such a cornerstone of the theory of relativity that's considered to this day one of the most important results about Einstein's equations. Okay? So if Einstein is often called the father of general relativity, Choquet-Bruhat is definitely the mother, okay, because of her fundamental contribution. You can read about her life in a memoir that she wrote, A Lady Mathematician in This Strange Universe, and there she tells the story of how she tackled this problem of solving Einstein's equations. Okay? The basic story is that this problem was suggested to her by another mathematician called Jean Leray when she was a graduate student. So she went back to her advisor and said, look, I want to work on this problem. And he was not very supportive. He said, no, that's too difficult. Don't do that. Fortunately, she didn't listen to her advisor, went ahead and tackled the problem anyway, and finally provided an affirmative solution to this question of solvability of Einstein's equations. So I guess the moral of the story here is that don't always listen to your professors. Okay, so we talked about Einstein today and his equations, and of course, he made a fundamental contribution, but I don't want to give you the impression that he did it all alone, okay? There were many other people, some of them listed here, some not, who also made fundamental contributions to this topic that we discussed today, okay? So science is a collective enterprise, okay? We're always relying on the results of others, okay? So this idea that you see in movies of the completely lonely genius, that's a myth, okay? We're always relying on things that other people did as well. So today, I talked about Einstein's equations, and for the sake of time, I had to make some simplifications, right? I was very explicit about some of the things that I was sweeping under the rug, but I try my best not to dumb things down, okay? I try to really get to the concepts and explain them as clearly as I could. And remember what I told you before, okay? So when you see some complicated math formula, in the end, it's just a language that you don't speak, the same way that you might see something in Mandarin or in Russian or in Greek and don't understand, okay? It's just a matter of learning the language. In the end, math and physics are not very hard. Life is much more complicated, right? And on that note, I want to thank you for your attention.
All right. Thank you, Dr. Disconzi. Questions? Nobody has any questions, right? Where to start, right? Oh, we've got someone else bringing the mic around. So we're passing the mics around so everybody can hear, including the folks watching on YouTube.
This is probably a dumb question, but because of gravitational lensing, is it kind of impossible to hide behind a star or black hole that's big enough because your light will always bend around it and be visible to somebody on the other side?
Okay, first, there's no such a thing like a dumb question, okay? All questions are important. And the answer, the precise answer to that question is going to depend on the mass of the objects and where exactly you are positioned, right? So if the object you want to hide from is here, and you are here, it's possible that you have gravitational lensing where these things curve and pass far away from where you don't want people to detect you, okay? And remember, these gravitational lenses typically can only be detected or are only significant when the objects are very massive. For example, right now there is gravitational lensing happening on the line between the two of us, but it's so faint that for all practical purposes, right, we can think that it's a straight line. So if you want to hide from me here, you don't have to consider no gravitational lens. You can just think, oh, it's a straight line, I'm just going to get out of his line of sight. Okay, so yeah, it is possible. It's going to depend on the exact specifics of where you are, the mass, and where is the source you want to hide from. Okay, does that answer your question?
Yeah.
Okay.
I have a question as well. There's no stupid questions, but this just might not make sense because maybe I just didn't understand. When you were talking about you don't need more dimensions in order to understand the math of a curved space, the thing that confused me is that the example you gave was drawing from something that was in deeper dimensions. So were you speaking only of the math, or were you speaking just generally we don't need to conceptualize those higher dimensions? Because it seems to me like...
Yeah, so...
Yeah.
Okay, so in general you don't need, but what I was trying to motivate is that if I just came here and said from the very beginning, I'm going to declare that this is a curved geometry by defining the rules such that that would not make sense. So where you're taking that from, okay? Right? So I was trying to motivate how first you could project something from higher dimensions to 2 dimensions, but after I project, like in the case of a map, forget the projection, forget where it came from. Somebody just came and handed to you this new geometry, and it makes sense on itself, okay? So I was trying to motivate because unless you're a mathematician, if I say I'm going to define this new geometry with these rules, and I'm not going to tell where it came from, that might sound too artificial. So I was trying to just motivate how you could take a sphere, project on the plane like you do with the globe, but now you have the map, and if you look at the map and look at the trajectory of the planes, you say that's a curved trajectory, but the map doesn't need the 3rd dimension.
Okay, so to understand the... Okay, okay, so that makes sense. But in reality, are we dealing with a higher dimension, like in the physics of it, like not necessarily?
As far as we know, no. Okay. There is a little caveat about space-time that I mentioned. So really, we have to talk about 4 dimensions, 3 spatial dimensions and time dimension. And the curvature we talk about in Einstein's equations is really the curvature of space-time. Okay. But then those 4 dimensions, they do not need a 5th dimension. So as far as we know, there is no higher dimension in our universe. There are theories about higher dimension, but within general relativity, everything is described only in space and time. Okay, so we don't need that. Okay, so
What is the limit to gravitational pull? Like, would galaxies thousands of light years away have a gravitational pull at all?
okay, so 2 things. First, let me remind you, I'm not an astronomer, right? So that's a question for maybe Billy. But okay, so when you're talking about things very far away, for most purposes, Newton's law is a good approximation. Okay, so for example, if people are modeling, like say, the motion of some galaxy very far away, they basically just use Newtonian physics, and then the distance, the gravitational pull, decays like the distance to the power 2, the distance squared. Okay, so I told you about the masses, but the other ingredient in Newton's formula is that the further they are, the weaker the gravitational attraction. Okay, and he quantified how this is the inverse of the square of the distance. Okay, so to answer your question, if a galaxy is very far away, the gravitational pull that you're going to feel is very, very weak because the distance is very, very large. Okay, does that answer your question?
Yeah. Yes, thank you.
So when you were talking about the nuances of that you like said that you weren't going to mention it was because it was too long, about acceleration and gravity and how in some cases it might not be exactly the same. So if you're in a spaceship, like if I was in a spaceship that was moving at 148, if it had like 148 G's worth of acceleration, I'd die because that's only the thruster that's pushed. It's only the thruster that's moving. The rest of the ship's not moving. It's being moved by the thruster, which would then cause me to go to the back of the ship and die.
Mm-hmm.
But what if every single atom inside the ship was moving with the exact same acceleration? Like suppose there was a black hole, and suppose that I was being pulled towards the black hole, and so gravity is pulling every single atom towards the black hole with an equal amount of acceleration. Then I wouldn't really feel anything, would I?
Okay, that's a very good question. So the example of the black hole is actually good, and that's the reason why this statement is not exactly true, because if you're a black hole and I'm here, and I'm being attracted in this direction, you see, because the closer I am to the black hole, the more curved the space-time is, so like the quote-unquote force of gravity is stronger. So what happens is that the atoms in front of my body are going to feel a force that's greater than the atoms on the back of my body, okay? And if the gravitational pull is very strong, that's just going to rip my body apart. That's what physicists call spaghettification. You're like become as a spaghetti as you approach a black hole, okay? And that's the reason why this statement is not exactly true, because you could distinguish between an accelerating spaceship and a gravitational field by these tidal forces, by comparing the forces between one part of one body and one part of the other body. But for that, you need an extensive body. You need a body that has extension. Mathematically, now you can do everything just as an infinitesimal point, and then there is no difference, right? So you can reformulate things like in these purely infinitesimal things, then there's no difference. But in reality, there is a difference because every body has extension, and different atoms are going to feel differently the force of gravitational. Does that answer your question?
Yeah, I guess I did for a second forget that the curvature is more pronounced forwards, but yeah.
Cool.
If a large object has curves the space around it, does not a smaller object also do that to a lesser degree?
Exactly. So that's correct. I kept talking about the sun, this very massive object, because those are the cases where the effect is detectable. We can actually see with our instruments. Right now, I'm curving space here, but you don't feel that curvature, okay? So we are all curving space around, but it's very tiny defect. So again, the difference between Newton's theory and Einstein's theory is going to be something significant only in extreme situations, like black holes, neutron stars, supernova, and things like that. Okay, for most purposes, the difference is so small you can barely see. So who was asking the question? Did I answer the question? Okay.
Hi.
There's one here. Okay.
Hi. I loved your talk. I'm coming from a very different background. I have a PhD in English where there are more questions than answers.
Okay.
So I wanted to ask about, you started your talk with a question mark and you ended with an answer. And I would just love to hear a little bit about like what it means. What is the significance of answering these kinds of questions in this world, right? Like what does it mean to have Einstein's equations solved? Like if you could just kind of help me to understand the weight of that.
Well, I could talk the whole night about that. I think, first of all, I think that's very subjective. People pursue science and math for different reasons, right? So I cannot tell you what exactly all mathematicians are doing when they are trying to solve an equation, right? For me, and that's something discussing my book, right? When I was growing up, I always liked puzzles. I always like, these logical puzzles and this kind of thing. So for me, it's a little bit like, what kind of hidden structure is behind these equations, right? There is something hidden there. It's not just an arbitrary thing, right? So again, if I just write an arbitrary equation, there's going to be something ugly with no structure. But for me, certain equations, they have some structure. There is the geometry, there is the analysis, there is the physics. There's a lot of structure behind these equations, and I'm trying to see how these different structures fit together. Okay, so solving the equation, okay, that might be the end result, but the thrill is really in the process, right? It's like, so I know that's not a very precise answer, but again, as I said, your question, something that I could talk the whole night about it, and different people are going to give a different answer to your question.
Similarly, I had a question about kind of towards the end of your presentation. I really liked how you phrased that like science was built on the backs of so many people. I don't know if you could go to that slide. I was really curious in the contributions of the two women that were on that screen, and if you could share like what their role was in building up Einstein's work.
Okay, so hold on. Okay, maybe it's better if I do the following. I guess I can go here and then, okay. Yes, so Emily Noether, she actually made fundamental contributions not only to relativity, but to many areas of mathematics and physics. And basically, she's the person who first realized that conservation laws are very important, right? So we talk about conservation of mass, conservation of energy, conservation of charge. All these concepts were the first person who really understood how fundamental they are for physics. That was Emily Noether, okay? So everything related to conservation. So there are some theorems, Noether theorems, that we teach like in undergrad courses that have to do about conservation of quantities. And she was the first person to realize that. And that turned out to play an important role not only in relativity, but in many areas of physics. And then there are areas of mathematics that have nothing to do with application, like in algebra. People talk about Noetherian rings and things like that. Okay, so she made many contributions. Kovalevskaya, so these equations that Einstein wrote, they involve geometry, but when you are trying to solve them, we have to approach them from another point of view that we call partial differential equations. Okay. The first person to ever give a systematic treatment of partial differential equations was Kovalevskaya. She was the first person who realized that there are these equations that we call partial differential equations, and she kind of gave the first steps to build a theory about how to solve these equations. And just to your point, like, there are the only 2 females on this slide. So the sad thing, for example, Kovalevskaya, if you look at the literature, you're going to see her name spelled in different ways because she could not use her female name when she was published because she would not get published. So sometimes she would sign like Kovalevsky, which would be like the male version. Okay, so yeah, there are these sad stories, but the good thing is that she didn't give up. Right, she kept contributing, and she made many other important contributions to theory of functions and partial differential equations. Yeah. Just before, and don't forget Choquet-Bruhat, right? Also a great female mathematician who, as I said, is the mother of general relativity, right?
So when you describe, like as Einstein had said, which was because Newton had thought that space and time were separate categories that existed like independently of each other, but so Einstein had said that that space time is a single entity. Is this because time is essentially just the succession of causality, and causality can only transpire within space? Because if you had a hypothetical universe where there's no motion, therefore no causality, you don't functionally have time in any meaningful sense.
Yeah, so there are several ways you can take that question, right? So for the point of no motion, right, you could imagine that you still have fields in your space, right? So they don't have actual motion of particles, but the state of these fields could change over something that we call time, right? So
wait, the state of what?
If you have fields like the electron field, like quantum fields or electromagnetic fields and things like that.
Yeah, fields. Okay.
Now, of course, part of the difficulty of nailing down that question is because you're really asking what time is, right? And the honest answer is that we don't know, right? So there is this thing that we can measure, right? We call it time, but if you ask like what it means, in a fundamental sense, I don't think physics has a good answer for that. In fact, there are physicists that think time is an illusion, that doesn't exist, right? There are many theories of physics nowadays that propose that time is like something emergent. Then there was the first part of your question. Okay, so yeah. Now, Einstein, he was actually thinking about the problem of simultaneity, right? So there were certain inconsistencies that people were observing between the notion that time is universal, that everybody feels the same time, and the way that the equations of electromagnetism, which are called Maxwell's equations, behave, right? So, and either Maxwell's equations were wrong, and there was a universal time, or there was no universal time, and Maxwell's equations were right. And Einstein actually took the equations very seriously, right? So he had this thing, he would take the theories very seriously, right? So no, these equations, there is nothing that we know from experiments or from their mathematical foundation that tells us that these equations are wrong. So these equations must be right, therefore time cannot be universal, right? So he had this kind of leap of faith. But that was even before general relativity. That was in the concept of special relativity, okay? And then later on, he kind of upgraded this notion to general relativity, okay?
Doesn't special relativity deal just with flat Minkowski space?
Yes, exactly.
But then general relativity also includes the curved space.
Yes, that's correct.
But then, I know part of it is when space changes, time can also change. Like when gravity becomes stronger, like closer to a black hole, for instance, time, would start to pass more slowly relative to time far away from a black hole. And it's similar with velocity. Like as your velocity increases, as your Lorentz factor increases, time starts to kind of slow down.
So you have to be careful with the statement that time slows down or speeds up, because those you can only compare times if you have a common reference frame, right? But if you don't have a common reference frame, you cannot. So there are all these things that we think of. Time is slowed down, time is speeds up, but those are always statements about local observers. Okay, so you cannot compare the times between different observers if you don't have a common frame of reference for both of them. Okay, but yeah, so but what you said is basically correct if you kind of take this into account.
Yeah, what I meant was like if you have a clock in one area compared to a clock in another area, the clock would tick slower by comparison.
Yeah, that's a phenomenon that's measured. So he's referring to the fact that for example, if you look at a clock in free fall, okay, just under the state of gravity, that's going to experience a passage of time that's different than a clock that's, for example, sitting on the ground. Okay, basically, you can show that observers that are in free fall, right, that are only subject to the gravitational force, which means no force, right, in free fall, they're going to have a longer passage of time than the observers that are moving relative to them. Okay, so for example, if I throw an object, okay, and this object spends some time, goes up and it goes down. So all this time is just under the force of gravity, it's in free fall. And this object is carrying a clock, and I synchronize my clock here. Okay, so I throw this object, it comes down, and when it comes, I compare the two clocks. It looks like this guy, the one that I threw, experienced more time than the one that I was holding in my hand, okay? Because it was like under free fall. And that's an actual effect that people measure with atomic clocks. But of course, it's very small. It's very, very tiny, okay? To be something that we as humans would experience, we would have to be free falling near a black hole or something like that.
All right, let's thank Dr. Disconzi for another wonderful presentation. If you all have any other questions, he'll be hanging around for just a little bit. We have cloudy skies this evening, but if you've never been up to see our main telescope, the Seifert telescope, I'd highly recommend going up. Dr. Bob and a few of our other volunteers are going to be up there, and they can tell you all about it. And then finally, we've got a little drawing that we're going to do for Dr. Disconzi's Who Me book. So if you got one of your tickets when you came in earlier, go ahead and pull that out. We're going to do a drawing for 5 of the books.